Can fish or other marine life exist under the ice of Europa or Enceladus? Can we be visited by an alien spaceship but with no pilot? What is the most common misconception about Hawking radiation? And in Q&A Plus, which sci-fi book best describes our world in a few hundred years? All this and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Aaron Sokol. A few years back, I saw a fireball streak very rapidly across the sky and explode right near the full moon. It was brighter than the moon, and I briefly saw pieces flying off. How big was it? So you might be surprised to learn that when you see a shooting star, a meteor, they're actually very small. So like when you go outside and you watch, say, the Perseids meteor shower, and you see this incredible streak of green that goes for half the sky, that thing is probably a little bit bigger than a piece of sand. And when they get bigger, maybe a couple of centimeters, maybe fist-sized, that's what you probably saw. Those are fireballs. And they can be, up to about a meter. Once you get to the meter size, then they turn night into day. They're really dramatic. But what you saw, probably in this size, probably smaller. And yet there's so much energy in those meteors as they're entering the atmosphere that they just cause that enormous sky show. Fireballs are rare. I've seen one in my life, and I've watched a lot of meteor showers. And hopefully, like a lot of people who are watching this right now, you've experienced this time. Like if you're lucky that the whole landscape turns to day or is very lit, and you can see it snap and crackle and pieces pop off and like kind of breaks into chunks as it's entering the atmosphere. And that's how you know there's something pretty serious. Enthusiastic astronomers can spend their whole lives and never see a fireball like that. So congratulations, that's really lucky. J. Lambert, why do scientists seem so skeptical that fish or larger sized life couldn't be in the salty oceans in the solar system, perhaps in the oceans of Europa or Enceladus? I always make the joke that we want to go to Europa to meet the European space whales, but the reality is that there are going to be things that are going to limit the size of the life, the amount of biological material that can be present in Europa or Enceladus. And I haven't heard the specific calculations on Europa or Enceladus, but I have heard the calculations on Titan. And Titan is another world like both Europa and Enceladus. It has a subsurface ocean, a thick layer of ice. It's the second biggest moon in the solar system. It has probably subsurface volcanoes that are spewing gas and chemicals into the water. And then you've also got all of the organic molecules that are on the surface of Titan, and they're probably finding their way down through cracks into the ocean underneath. You have all of the raw material that you require for life. But the question is, how much energy is being put into the system that then life can use? And the problem is that there's just not enough. There's not enough usable energy. When we are here on Earth, we are experiencing something like 1,000 watts per meter, an enormous amount of energy. And then that allows plants to grow. That allows animals to eat the plants. That allows bacteria. That allows all of this kinds of life because of the huge energy density that we're experiencing here on Earth. If we change the sun to a red dwarf star, it could still be warm enough, but the wavelengths of the light would reduce the amount of energy, density that's available on the surface of the planet. And we might not even be able to have plants grow under red dwarf light, or it would be a reduced amount of life on the surface of the Earth. But when you're looking at just pure chemical energy that you're getting from volcanism, it's not very much. And so people calculated that I think it was, you could have 10 million bacteria or one small dog. That's how much life would be supported by the chemical energy that is going into the subsurface oceans on Titan. And so you can kind of assume it's probably the same on both Europa and Enceladus, that there's just not a lot of energy. And so you just aren't going to get microbes growing near the volcanic vents, fish eating those microbes, being eaten by bigger fish, and then of course becoming meals for the European space whales that you don't get bigger than bacteria. But even bacteria would be amazing to find. And so that's why people are skeptical, is that there's just not enough energy available for life to grow into larger body sizes. Santiago T, I understand how gravitational lensing causes a warping of space and thus light gets bent. What I don't get is where the magnification comes in. Could you explain it? Sure, it's the exact same way that a lens works or that a mirror works. That, if you imagine some object, a tree, right, is really far away, and it's, photons are coming off of the tree in all directions, and then you put a lens on your side, you're taking the photons that are coming off the tree that would have missed your eyeballs, and you're redirecting them back into your eyeballs. And so you're seeing more photons than you would normally be able to see with just your eyes. And the bigger the mirror, the more of those photons that would have missed you, you're now redirecting in. And it's the same thing. A galaxy cluster warps space around it so that photons that are traveling, that would be sort of moving away from us, have to follow this curved path around the galaxy cluster and converge back on your eyes. And so you get this magnification process. It's time to shout out all the new $5 patrons and above: John Regal, Robin Beach, Travis C. Porco, Jack Brohammer, John Breidenbeck, Jamie Gaspard, Joey C., Jeff McDonald, Bob Blaskowitz, and Bill Bradford. Join the club at patreon.com/universetoday. Taco1011, reading The Dark Forest. Is it possible that an alien spacecraft visiting the solar system won't have a pilot, have no discernible outgoing radio transmissions, and will behave like the water drop? Okay, so that is very inside baseball here. We're talking about The Dark Forest, which is the second book of the Three Body Problem trilogy. And I would be spoiling if I explain what the water drop does. So I'm going to answer your question, which is it possible that an alien spacecraft visiting the solar system won't have a pilot? And yes, almost certainly. A spacecraft visiting the solar system won't have a pilot. That if you want to be able to explore the entire galaxy, you need to leverage self-replicating robot probes, von Neumann probes, where you send a spacecraft out to the asteroid belt, it picks up all the raw materials, makes copies of itself, sends copies to all the various nearest star systems. They arrive at these star systems, they find the asteroid belts in those different star systems, make copies of themselves, go to other star systems. And that it's this completely automated process, which then has them explore the entire Milky Way. And when you consider the size of the Milky Way is, say, about 120,000 light years across, and we are like halfway in between the center of the Milky Way and the outskirts of the Milky Way, and let's say we were going to send a space probe that could go at 10% the speed of light, then it would just take about 1 million years for one spacecraft to multiply like bacteria, like fungus, like yeast, to every single star system in the entire galaxy. And then each of these, as the spacecraft arrives, it builds a big transmitter and starts sending home data back to planet Earth. And then we are collecting in this giant database all of the planets, all of the stars, all of the interesting precursor artifacts that we find in all these different star systems, all of the alien life that we find. We just collect it all in one big database. And after 1 million years, we will have completed the database, the Encyclopedia Galactica. We will know every nook and cranny of the entire galaxy. And that will be useful just for like our knowledge, or would be useful if we decided, okay, what are the best planets? Which are the ones we want to send spacecraft to actually try and colonize and move to, or send settlers to? So there's real value to do that. And so one of the sort of thought experiments that you have is, because that's a thing that we are likely to do, then we would expect other civilizations to do that to us. Now, for those of you who are steeped in this idea, one of the big challenges is actually the keeping your spacecraft coherent over long periods of time, because you're going to be making copies, and that those copies are going to suffer radiation damage and so on while they're going through space. And so they're going to need to have some form of error correction. And so there was a paper that we reported on about a year ago where this is actually a big problem. If you're going to try and have a spacecraft that's going to be able to go for, a copy of a copy of a copy of a copy for a million years, that it is going to start to decohere and it's going to lose a lot of its programming just through cosmic rays. They're just going to be slamming into its memory system and giving it problems. And so we need to come up with some kind of a solution to make the spacecraft able to handle that kind of long-term copy paste. And that's where we would look to life. Look at the way life is able to adapt itself to changes in its environment over time through evolution. It might be that we develop an evolutionary algorithm for our spacecraft so that they can then evolve as they move from world to world. And who knows what we're sending out into the cosmos. But yeah, that's a thing that we would expect. Would it move like the water drop? It depends on what your programming is. Read the book. For those of you who don't know what it's talking about. Eric Poot. Hawking says black holes will evaporate when particle-antiparticle pairs pop into existence at the event horizon, and only antiparticles drop down into the black hole. Wouldn't the split be even, keeping the black hole stable? So this idea of Hawking radiation, that you've got this black hole, the event horizon, you've got virtual particles that are popping up at the very edge of the event horizon, and normally those virtual particles come together and annihilate, but in this case you've got a black hole, one falls into the black hole, the other is able to escape and go out into the universe. This somehow makes the black hole evaporate away because you can't have matter appearing out of nowhere, and the black hole has to give up some of that material. That is a bad thought experiment that Stephen Hawking gave, and knew that it wasn't a good thought experiment, but he wrote a book about it, Brief Moment History of Time, and it just stuck in the public consciousness. And so we get these kinds of questions from people because, like, obviously the idea that Hawking is putting into your brain is starting to come apart at the seams, and you're like, I don't get these pieces. How can light be coming off of the black hole and yet the black hole's getting smaller? I don't really understand. And what if okay, so that's not what's happening, and that's not what causes a black hole to evaporate. So I want to take you on a journey of a completely different way of thinking about Hawking radiation, one which will make your question irrelevant, and yet is a much more accurate picture of what's actually happening and what's causing a black hole to evaporate. So the first thing we have to consider is this idea that space is filled with fields, and that, you know, there's various fields that are associated with all the different particles, and that when you accelerate through space, through fields, you experience radiation. And it's called Unruh radiation. And this is just like one of the intrinsic properties of space. As long as you're accelerating through space, you are experiencing radiation. And we know that the equivalence principle says that you can't know the difference between accelerating or free falling. That, you know, in a gravity field, that you can't tell whether you are sort of floating in space or whether you are accelerating down into a gravity field, that the experience is equivalent, right? And that there's no way to tell the difference. You know, if you are in an elevator and the elevator is like the TARDIS and it is accelerating through space, and because it's accelerating, you are experiencing the force of gravity on the floor of that elevator, and it feels just like exactly like gravity, or the elevator is sitting on the surface of the Earth and you're experiencing the same amount of gravity. And there is no way to tell the difference. That is because the acceleration through space and the acceleration caused by being in a gravity well are equivalent with each other. And so when you take that idea of them being equivalent to each other, you have to take that to all of the different ways that these things play out. And one of these is that Unruh radiation. This idea that when you're accelerating through space, you experience radiation. And so when you are in the presence of a gravity well, you are experiencing radiation that is coming in the exact same way as when you're accelerating through space and time, space-time. And this effect is non-existent. But when you are, you know, very close to a black hole, an extremely dense, massive object, then this radiation can become present, or, you know, detectable, theoretically. And so back to that sort of idea that of what Hawking was saying was that, you've got this radiation, it can't come from nowhere, and nobody's moving, right? Nobody's accelerating, nobody's expending energy to move through this gravity well, or nobody's experiencing energy, caused by this gravity well. And so the black hole has to give up some of its mass to create that energy, that Hawking radiation. And so over time, the black hole gives up more and more of its mass, turns it into radiation. And the amount of radiation that you experience is inversely proportional to the mass of the black hole. So that is the answer. And so when I go back to your question, you can see it doesn't really matter, right? That there are particles, mostly photons, that are coming off of black holes that are the result of this sort of equivalence principle that force the black hole to give up mass. And the thing that's really interesting is that this Hawking radiation probably happens to everything. It probably happens to neutron stars. It probably happens to white dwarfs. It probably happens to us, that on the scale of 10 to the power of 100 years, we will evaporate because of the gravitational potential of our mass. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. And this week's bonus question, what sci-fi book describes our world in a few hundred years? I'll put a link in the show notes. All right, those were all the questions that we had this week. Thank everyone who put your questions into the YouTube comments, everybody who joined me for the live show. Now, if you're watching this just when we released it, the next live show is going to be on Monday, October 6th at 5 p.m. Pacific time. And you can just convert that to wherever your local time zone is. Now, I'm going to talk about a huge improvement that we've made to the podcast. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Braley Griffin, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailock, Cy Nelson, David Varibath, David Gilton, David Matz, Evan Pro, Greg Feely, Hudson Moore, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Spitz, Michael Purcell, Modzo, Paul Roebuck, Rank Kaidu, Richard Williams, Sean Sargent, Stephen Fallon-Melly, Team 49, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Now, you're watching this video on YouTube, but many people much prefer to get their content via podcasts, like me. I like podcasts. And, partly it's just because you can subscribe to the podcast that you like, and then they show up automatically, and you can listen to them while you're working out or while you're doing the dishes or you're in a commute. And, yes, what we make is better in video form because we put all of the additional content with it, but still, it works pretty well as a podcast. Now, what we used to do was take the video that you're watching here on YouTube, and then we would rip the audio from that, and then that would be the podcast. But we actually do another version called Q&A Plus, which has one additional question that you hear me mention this, and then we release that over on Patreon. And we've decided to release that in the podcast as well. So now, if you want the version of our content with an additional question or an additional story or a longer interview, it's still available completely for free. And now you can get that on Patreon, or you can subscribe to our podcast and get it there. And of course, all of this is completely free. None of this has any ads. There's no reason not to go and subscribe to those various channels. All right. Hope you enjoy that, and we'll see you next time.